Equilibria. So 3.1, behavior of acids and alkalines. Okay, so first point, they said when acids and alkalines are added to water, they dissociate or ionize, and a dynamic equilibrium is set up. Okay, so how is the equation looks like? We need to know about that. So that's why you look at number two. Number two here, general equilibrium of an acid. So you can see this is the acid Ha. Ha is the acid, where they assume that acid always have hydrogen ions there in the acid molecule, and the A is the anion. So this Ha is the acid molecule, react with water, and then what happened then is acid donate the hydrogen ions or the proton to the water, and the water form H3O positive. That is called hydroxonium ion. Okay, hydroxonium ion. So if you feel like you don't want to write hydroxonium ions, then you can simplify it to H plus. So you can use H3O positive or H plus. And the other thing is plus the anion. So if you are using H plus, then the equation is good to write in this way. So where you put like this, Ha, which is the aqueous, and then we have H2O on top, H plus aqueous, and then A minus aqueous. So we can put it in this way. Okay, so if you want to write H plus instead of H3O plus, then you write your equilibrium equation in this way. So this is what they mean in the first time. Acid added to water, they dissociate or they ionize, and they form a dynamic equilibrium. So dynamic equilibrium, we must use this kind of arrow. Okay, we have to use this kind of arrow. So in that case, that means they don't 100% change to ion. That we still have some acids remain as molecule. So that's why it is reversible. Okay, so now you see strong acid. A strong acid is where it is irreversible. Okay, irreversible. So if it is irreversible, that means 100% change to product. 100% change to the ions here. So 100% of the acid molecule ionize in water to form H plus and anion. And equilibrium position is to the right, and that dissociates completely. So if that dissociates completely, right, we don't use Kc anymore, or we don't even use this. This is the new formula. We don't use Kc anymore because they all change to product, right? Your acid molecule has zero concentration. You put zero concentration at the bottom, it end up with undefined. So that's why if it's strong acid, we don't use Kc. We don't apply this formula on strong acid, which is irreversible. Okay, so it is for weak acid. The Kc here is for weak acid. Okay, so but they put it here just to make it complete, and dissociates completely. So they dissociate completely. That means if the acid is monobasic acid. Monobasic acid means monobasic. Monobasic means the acid ionize and form one mole of acid molecules form 1 mole of hydrogen ions. That is monobasic acid. So if they are monobasic acid like HCl, then the concentration of HCl is equal to the concentration of H plus. So as in here, okay, as in here, concentration of HCl is equal to concentration of H plus. As it is monobasic, right? So one HCl contribute to one H plus. But if this is sulfuric acid, which is dibasic, H2SO4, then the concentration of H plus has to be double. Because dibasic, one mole of dibasic acid, H2SO4, for example, ionized to form 2 mole of H plus, double. Then this statement is not true already. This statement is not true for dibasic acid. Okay, so be careful with this statement. So this statement is just for monobasic acid like HCl or like nitric acid, HNO3. Okay, so let's see weak acid. Weak acid. So of course I just put it here just to make sure. For strong acid, HCl, HNO3, and H2SO4. So basically, these three are the famous examples for strong acid. Now let's see weak acid. So weak acid, the famous example is like CH3COOH. This is the famous example. Okay, so of course you have others. So I just put one first. Now, for weak acids, when they react with water, they ionize partially in water. Equilibrium position is to the left, meaning that when they achieve equilibrium, we still have a lot of acid remain as molecule, and only a small percentage change to ions. So that's why, because of that, equilibrium position is to the left, meaning that there is a lot of undissociated molecule. Okay, so dissociates partially, and because of that, the concentration of acid is not same with the concentration of ions. Okay, so it's not same. Imagine if you use 1 mole of ethanoic acid. This is ethanoic acid. If you use 1 mole of ethanoic acid, you dissociate it, maybe you just get about, let's say, 5%. Okay, 0.05 mole per dm cube. 0.05. Okay, the concentration is 0.05 for ion, and the concentration for acid is maybe 1 mole. Okay, so it's different, not like this. The concentration is 1 mole. After dissociation, this is also 1 mole. They are same in concentration. These are not same. Okay, so because they don't dissociate completely, so that's why they are not same. Now you see Kc. Kc is the formula that we learned in AS chemistry. So we put the concentrations of acid on top, as you can see here. Concentrations of acid, concentration of ion. Concentration of ion. So the H plus and the anions. And at the bottom, we put the concentration of the acid molecule together with water concentration. But the thing is, concentrations of water is a troublesome thing here. Concentration of water. For example, let's say, if they give you, let's say, example, 1 mole per dm cube of CH3COOH. So in that situation, right, you will feel like, I know the concentration of HA. I know, because HA is basically this one mole per dm cube. So I know the concentration of HA. But from this sentence, right, I don't know the concentration of H2O. That is the problem. Concentration of H2O is a problem here. We don't know the value. So because of that, we have to use a simplified version, which is without H2O. Okay, so of course the H2O here doesn't really important here. Okay, doesn't really important because we focus on acid change to ions. So this one, like what they said here, they said water dissociates very slightly. They change a little bit to ion, change to H plus and OH minus, just for your information. Just a little bit only. And because they dissociates very slightly, concentration remains constant. Concentration remains constant for H2O. And because of that, we can just ignore the concentration of H2O and we don't use Kc anymore because Kc must put H2O. So we simplify our formula to Ka. Ka, which is without H2O concentration. Okay, so if let's say I want to know what value is the concentration of H2O, we can count it one. Okay, so it's just for general knowledge. So what is the concentration of H2O in a normal solution? Okay, so you think like this, we know that 1 cm cube of H2O is equal to 1 gram. It's equal to 1 gram. So you want to change it to mole per dm cube, it is not too hard. Yeah, not too hard. So mole equal to mass over molar mass. Molar mass. So the mass is 1 gram, for example. The molar mass is, hydrogen is 1 times 2. Then oxygen is 16 times 1. So which is 1 over 18. So this is the mole. Concentration is mole divided by volume. So the concentration of H2O, which is mole, divided by volume. So what volume are we talking about? Is 1 cm cube. So 1 cm cube, you want to change to dm cube, you have to divide by 1000. 1000. And from here, we just press calculator. 55.56 mole per dm cube. So imagine the concentration is so big. You see, normally acid is just 1 only, 1 or maybe 0 point something, the concentration. But the concentration of H2O is so big. And after dissociation, maybe it is 55.555. Maybe they drop a little bit. So because of that, the H2O concentration, that dissociates so little, right? The concentration, we have to say that before reaction and after equilibrium, initially and the concentration initially and the concentration during equilibrium is just the same only. And hence, no point to put a constant there. So they eliminate. So they replace with Ka. And what is Ka? Ka is the acid dissociation constant. As you can see here, the acid dissociation constant, Ka. So they said can be used to compare strength of acids. So if you count the Ka, right, the Ka have some significance over here. So it represents the strength of acid, where the higher the value, the stronger the acid. So you can look at their Ka and compare. Okay, and compare. So for example, you see like ethanoic acid. The Ka is 1.74 times 10 to the power of minus 5 mole per dm cube. So you can see very small value, meaning that they are very weak acid. Weak acid. Okay, so I should have another example. Let's see whether I can find out another example so that you can compare. You can roughly know what value are they taking. So I try to find out another value. If I can see any, I just let you know, okay, so that you can compare a bit. Another famous acid here is like carbonic acid. Carbonic acid, which is H2CO3. H2CO3, carbonic acid. So the Ka, right, is just 7.94 times 10 to the power of negative 7 mole per dm cube. So from here, if you compare between ethanoic acid, okay, ethanoic acid, this value, and carbonic acid, this value, so we can apply our statement here, where they say that the higher the Ka, the stronger the acid. So this is higher in value. This is smaller in value. So this ethanoic acid is stronger than carbonic acid. Okay, so to understand this value, right, you need some mathematical knowledge, where the decimal point have to go in front for 5 times to form the actual answer in decimals, and this decimal point have to go in front by 7 times. So by moving forward by 7 times, you form a smaller decimals. So because of that, they have an alternative here. They said the Ka values are extremely small. So you see, it's kind of small, -5, this is -7, they are small. So negative log the value will give you pKa, and we use pKa to compare the strength. So for example, right, you want to change it to pKa, you need to negative log the Ka. So let's say we try to do it here. Okay, so let's say I do it at the side here. Example, pKa for ethanoic acid. We negative log the Ka of ethanoic acid, which is 1.74 times 10 to the power of -5. So we negative log the value. And after that, if you get a value which is easier to read, okay, so times 10 to the power of -5. So you will get 4.76. Okay. And example again, let's say carbonic acid. Carbonic acid. So the pKa is negative log 7.94 times 10 to the power of -7. And if I press calculator, then I will get 7.94 times 10 to the power of -7. So I will get 6.10. So this value is greater already. It's greater. So the carbonic acid pKa is greater than the pKa for ethanoic acid. And the idea is now in the opposite way, The smaller the pKa, the stronger the acid. So this is the smaller one. 4.76 is smaller, showing that ethanoic acid is stronger acid compared to carbonic. So you either use Ka or pKa to compare, where you have to know that Ka, higher value means stronger acid. pKa means smaller value, stronger the acid. Okay, so and now we have a equation or formula to convert. So you want to convert Ka to pKa, you negative log the Ka. But if pKa is given, you want to change it to Ka, you have to do 10 to the power of negative pKa. So that means, for example, if I want to convert here, okay, so this one, if I want to convert it back to Ka, so I just do Ka equal to 10 to the power of negative 4.76, and then if you get back the Ka that is given just now. So you will get 1 point. You will get 1.74 times 10 to the power of negative 5. You will get back the same value like just now. Okay, so now let's see this question. Calculate pH. pH. So we haven't learned pH yet. Let's move on to the next part first. The next part, which is here on the right hand side. 3.2 pH scale. pH scale. So we heard of pH long time ago, where pH less than 7 means acid, pH greater than 7 means alkaline, pH equal to 7 means neutral. So we learned pH last time, and now we have to take the formula of pH. So the first point here, okay, let me cut away these words. Okay, so let's see. The first point, strength of acid depends on the concentration of hydrogens. Okay, so of course, this is common sense. Like the stronger acid ionize to form higher concentration of hydrogen ion. So this should be a logic or a common sense for us if you understand chemistry. So more hydrogen ion means stronger acid. Now, second point, use negative log of values as they are very small. Okay, the wording here is a bit weird. So, what are they trying to mention here is actually the concentration of hydrogen ion is very small. So we negative log the hydrogen ion concentration to give pH value. So they are trying to say this. Okay, so if you realize this idea is similar to just now. Just now, right? Our case here, they said the Ka is very small. Here, values of Ka are very small. So you negative log to give pKa. Okay, so now they are mentioning something similar. The concentration of H plus is very small, so the negative log the concentration of H plus to give pH. Is it similar idea? Okay, so when you negative log, right, the situation become opposite already. Become opposite. Same like just now, when you negative log the Ka, the situation become opposite, where they are like the smaller the pKa, the stronger the acid. Here, the smaller the pH, the stronger the acid. You have to see the relationship between this and that. But don't misunderstand and say that are they same or not? Are pKa same with pH? They are not same. Okay, they are not same. They are similar here and there. You don't assume that, okay, you don't assume that something like this. You don't assume that like I get pKa equal to 4.76 for ethanol acid. Can I say that pH is 4.76? So actually it's not. It's not. So don't misunderstand until you feel like it is the same value. Okay, it is the same value. It is not the same value. They have similar concept but not same in value. pH and pKa is not the same value. Okay, so be careful with that and make sure you don't misunderstand. The way that they form the formula are similar. Okay, now you see the formula here. You just need to, okay, as in here, you just need to negative log the hydrogen ion concentration, then you get pH. Okay, you get pH. Or in the other way around, if hydrogen ions concentration is to be found, you just do 10 to the power of negative pH. Similar with this one, you want to find Ka, right? You do 10 to the power of negative pKa. And this one 10 to the power of negative pH. Similar concept, a similar formula. But don't think, never assume that they are same in values. Okay. Now let's come back to this question. So this question we just discussed only. Okay, so here, calculate the pH of 0.1 mole per dm cube of ethanoic acid. Ka equal to 1.74 times 10 to the power of negative 5. Okay, so you want to count pH, right? So first of all, you may think of pH equal to negative log base 10 concentration of hydrogen ion. But the problem is we are not given with this concentration of hydrogen ion. They give you concentration of ethanoic acid, but we have to know that concentration of acid is not same with concentration of hydrogen ion. Not same for weak acid. Ethanoic acid is a weak acid. So when they give you concentration of acid, it doesn't mean that concentration of hydrogen ion will be that value. It is not. It is not the same value. Okay, concentration of acid is not same with concentration of hydrogen ion, and because of that, we need to find it out. We use this formula. And we want to find out the H plus concentration. Okay, so to use this formula, let's say as a practice, I write down the equation. Okay, I write down the equation. So, like what I mentioned just now, there are two versions on writing out the equilibrium. The first version is here, where you put H2O, and then by right, this one supposed to become H3O positive. H3O positive, as in here, H3O positive. This is the first version. You put H2O here, here become H3O positive. The second option is you put the H2O up here, then it becomes H plus. So I'm going to write the second version. I put H2O on top. So our equation, CH3 COOH equals dissolve in water and ionize to, okay, so let's say I follow the formats given. So I start with positive ion, H plus, CH3 COO minus. So based on our Ka formula, as you can see here, the Ka formula is given in this way. You're supposed to put concentration of H plus multiply with concentration of N ion divide by concentration of acid molecule. So the Ka, right, supposed to be H plus multiply with CH3COO minus, this is the N ion, divide by the concentration of CH3COOH, the acid molecule. But the thing is, we have to know that these two will have the same number of mole. We have the same number of mole. So for example, right, if one CH3COOH dissociates, then they will form one H plus and one CH3COO minus. So these two have to be the same number of mole. Okay, same. Okay, so of course they are same because initially it doesn't have any ions in the water. So then this one, the acid molecule, the ethanoic acid molecule dissociates and form same amount of H plus and CH3COO minus. Okay, so they are same. And because they are same, right, so you can just assume, let's say, the concentration of CH3, okay, maybe I put like this. The concentration of H plus is equal to the concentration of CH3 COO minus. Same. And you apply it to the numerator here, then it become, concentration of CH3 COO minus can replace by H plus instead. So this become H plus. This part become concentration of H plus, and because of that, the numerator become concentration of H plus power 2. So because the N ion have the same concentration with the H plus, so that's why it become power 2. And the bottom, right? The bottom, which is the concentration of the ethanol acid, I replace with 0.1. This value is given in the questions. Ka is given also 1.74 times 10 to the power of -5. Then from here, we just play around the fractions, and at the end, it will get concentration of H plus. Okay, so hold on, I just press calculator, and you multiply the two decimals and then you square root, then you get 1.319 times 10 to the power of -3. Okay, so that is the concentration of H plus. So once you get it, now we can start using the formula. So this formula is written at the beginning. Concentration of H plus, take negative log, then you get pH. Just now we don't know the concentration of H plus, and now we found it out already, and let's apply it. pH equal to negative log 1.319 times 10 to the power of -3. Okay, then we get the pH ready. Two point 88. 2.88. So that is the pH. So that's why I said pH and pKa are different value. Although the idea of getting the formula is the same, but they are not same in value. You see, pKa we get 4.76 for ethanol acid, but pH we get 2.88. So it's different idea. Okay, so you already know how to count the pH, and the process is quite complicated. And let's see more example. Okay, on this side, this chapter involves quite a lot of calculation. Okay, a lot of formula and calculation. Now, calculate pH of a strong acid. pH of a strong acid. Find the pH of this concentration of nitric acid. First of all, we need to know that HNO3 is nitric acid, and nitric acid is a strong acid. As you can see here, nitric acid, strong acid. So strong acid, I mentioned before, we cannot apply Kc on strong acid because at the end of the reaction, the concentration of Ha is 0. Okay, so we cannot apply Kc. If you cannot apply Kc, that means you cannot apply Ka also. For strong acid, we cannot apply Ka because at the end of the reaction, the concentration of Ha is 0. You don't use initial concentration. We use concentration, or maybe I don't want to make it that complicated first. So you just remember it. Strong acid, we can't use Kc or Ka. Okay, so even in this question, right, you will realize they don't give Ka or Kc. Okay, they don't give Ka or Kc. They just give you concentration only. Okay, concentration only. They give you concentration, which is 3.6 times 10 to the power of negative 5. So if this is the case, right, then how are we going to find the pH? So we use this concept. You see in the table here, the concentration of acid given, 3.6 times 10 to the power of negative 5, is equal to the concentration of ions. Concentrations of ion. So that will be good enough already. That means concentration of H plus is concentration of the acid. So I put it down here. Let's come back to this question. Concentration of H plus is equal to concentration of the acid, which is equal to 3.6 times 10 to the power of negative 5. Then we can do pH already. So you will realize the working is very much easier compared to just now, the weak acid, the ethanol acid. You want to count pH, you have to do many steps. But this one is very simple. Okay, we just negative log concentration of nitric acid. Then you get the value. .44. Okay, so if you ask me, why ethanol acid the pH so low and why this strong acid the pH so high one? Okay, so of course pH is affected by concentration. It's affected by concentration. This one has high pH because the concentration is very small. Very small. And this weak acid, the pH is lower because it used a high concentration of 0.1. Okay, so it's affected by concentration also, If nitric acid is using 0.1 mole per BNQ, for sure the pH is smaller than this value. For sure it's smaller than this if they are using 0.1. Okay, if nitric acid use 0.1, the concentration can go until 1. pH is 1. So that means if you want to know which acid is strong acid and which acid is weak acid, you make them to have the same concentration first. Then you can compare the pH. Okay, so if the concentration is different, so it is unfair to compare the pH. Okay, so that is the thing. Now let's move on. 3.3. 3.3. Ionic product of water. Ionic product of water. So why we want to learn about water? Because water dissociate also. Water, same like acid, dissociate also. Dissociate to ions. So first point, water molecules can function as both acids and bases. Why? Because to function as acid, the condition is you have to donate H plus, or you have to form H plus. To function as base, you have to dissociate and form. You have to ionize and form OH minus. So water can do that. As you can see here, one molecule, or maybe I look at this equation first before we continue with that point. Okay, you see the equation here. So this equation, water can dissociate or ionize to form H plus. So if they form H plus, then it fulfills the condition to be acid. If water can form OH minus, it fulfills the condition to become base. So that's why it can act as both acid and base, because it donates H plus, which is like acid. It donates OH minus, which is like base. Okay, so let's see here. One molecule base accept H plus from second one acid. So what are they trying to say is base will accept hydrogen ions. Okay, acid will donate hydrogen ion. So basically, in neutralization, acid donate H plus to the base to form salt and water. They are trying to say something like that. Okay, so they are talking about neutralization somehow. Okay, now let's see example. How water act as acid and how water act as base. Okay, so let's say if I have H2O plus CH3COOH, so it forms H3O positive. As you know, ethanol acid can donate proton to water, then water form hydroxonium ions after accepting H plus for hydroxonium ion. So I draw an arrow here. So H2O accept H plus and form H3O positive. And the ethanol acid, after losing the H plus, becomes CH3COO minus. So this one donate H plus and form CH3COO minus. So those who donate H plus act as acid, and those who accept H plus act as base. Okay, so this is where water act as base because water accept H plus. Water accept H plus, so water act as a base. Okay, so I call this 1. Now I give you another example. Equation 2. Water react with ammonia. So the ammonia will take the hydrogen ion from water to form ammonium ions. So if you see this equation, you will realize that the H2O donate H plus donate H plus to form OH minus, and ammonium accept H plus to form ammonium ion. So ammonia accept H plus to form ammonium ion. So over here, H2O who donates H plus act as acid. Ammonia who accept H plus act as base. Okay, so from here, from this example, you can see that the water molecule here can function as acid, as in example 2, can function as base, as in example 1. Okay, so that is how we explain it. Okay, why water can act as base, why water can act as acid. So it depends on whether it is accepting H plus or donating H plus. Okay, so it depends on that. Now they give you the water dissociation equation. H2O dissociate to form H plus plus OH minus. So because of water which dissociate, right? But they dissociate a little bit only, just for your information, as you can see at the beginning of the note. They dissociate a little bit, which is here. Water dissociates very slightly. Concentration remains more or less the same. Just now I mentioned also, the water concentration is 55.56. After dissociation, maybe 55.555 like that. Okay, maybe drop a little bit only. Okay, so we assume constant. Okay, we assume constant. So now, if you have this equation, this reversible equation, then you can find Kc already. Kc is product over concentration of reactants. Okay, but again, having H2O concentration at the bottom is something that we are trying to avoid in this chapter because of the same reason. We don't want H2O at the bottom because the concentration is more or less the same. Okay, more or less the same. Remain constant, which means concentrations remain constant. So we try to ignore it, then we have new thing. So here, same also. When you try to avoid H2O at the bottom, then you cannot use Kc anymore. You have to come up with a new formula, which is called Kw. Kw equal to H plus times OH minus, which is the numerator alone. This one we don't want already. So that's why we have a new formula. And yeah, they mention the same thing again. Concentration of water remain constant, hence can eliminate from equation, and we have a new formula which is called ionic product of water, Kw. Kw is ionic product of water, which only consider the concentration of H plus and the concentration of hydroxide ion. Okay, so now why we want to learn this? Let's continue first. At 25 degrees Celsius, the Kw of water is 1.00 times 10 to the power of negative 14. So this is the Kw. Kw at 25 degrees Celsius. Okay, so if this is the value, then how are we going to use it? Let's say, for example, okay, I put explanation at the side here. Example, you know H2O when they dissociate, although they dissociate a little bit, but we are still able to count one. So you need to know that, let's say initially they haven't dissociate, there is no concentration. So after dissociation, this is initial, initially there is no ions. So at the end, during equilibrium, water, a small amount of H2O will change to ion. So it become, let's say unknown, X. The concentration is X for H plus. But you see ratio here is 1 to 1. No number here means 1. 1 to 1. So if H2O form X mole per dm cube of H plus, then there should form X mole per dm cube for OH minus. Should be the same. Now, you want to count Kw, right? Which is H plus and OH minus. So this is X, this is also X. So Kw is, let's say we do it at 25 degrees Celsius. So Kw is 1.00 times 10 to the power of negative 14. This value is given just now, where it is here. Okay, it is here. You can see the red cursor here. So that value is given. I just replace here. Then you can find the X. So the X is, imagine it become X squared on the right. Then you have to square root and end up with 1.00 times 10 to the power of negative 7. That is the concentration of H plus or concentration of OH minus. Okay, so H plus or OH minus. So now, if we are going to find out the pH, right, that is not going to be too hard because we already know the concentration of H plus and we already know the concentration of OH minus. And then to find out the pH, it is easy. So the pH is negative log concentration of hydrogen ion, which is 1.00 times 10 to the power negative 7. And by pressing calculator, you will get 7. You will get 7. So, which is logic, you know. The concentration of water is 7. It's neutral. Okay, it's neutral. Yeah, okay, pH is 7. Okay, so neutral. In normal situations, the water has pH 7. Okay, now let's see more information over here. They said in this point, negative log throughout the equations. Throughout which equation? This equation. You negative log both sides. So they are saying that. And if you get this thing, and you get 14. You get 14. So which means what? Which means you negative log. Okay, I show the working here. You have Kw equal to H plus OH minus. They said negative log throughout the equation. That means negative left hand side and negative right hand side. So we negative both sides, and after that we have to negative log 10 for this value. This value 1.00 times 10 to the power of negative 14. We have to negative log that value. So let me write down first. Negative log 1.00 times 10 to the power of negative 14. On the right, I'm going to apply the logarithm formula, where when you have when you have log base 10 and two things multiplying, then it becomes log plus log. So it will become log base 10 H plus log base 10 OH minus. So this is the log concept. So after that, we press calculator on the left, we get 14. And imagine a negative you multiply to both, and you get negative log H plus, that is pH. Negative log H plus is pH. Negative log OH minus seems like we haven't learned before, but here I have to tell you straight away, it is POH. Negative log, okay, I write in blue color. So you have to know that this is for base. For base, negative log OH minus is equal to POH. For POH. Okay, so that's why we get that formula over there. Okay, so which is here 14 equal to pH plus POH. Okay, so next point, pH of an alkaline can be calculated using this formula. So you want to find the pH of an alkaline. So basically, you can use this formula. That means how to use the formula. You go and find out the concentration of OH minus first. Concentration of OH minus. Then you negative log to get POH. Then after that you put your POH here. Then you bring the POH to the left and you get the pH of the alkaline. Okay, so maybe one example lah, okay, for alkaline. So let's say, okay, I create one example, how to count the pH of an alkaline. So I need to find out the value first. Let's see whether I can get any value for, let's say, ammonia. Oh, okay. Hold on, I try to find it. If I can find it, then I will put it as an example here. If not, then I will just move on to the next page where there is another calculation also. Ammonia. Okay, so in order to find out the pH of an alkaline, so I need to explain a bit. How are we going to apply all the concept here on alkaline? So you will realize everything here are acids. Okay, are acids. So how about alkaline? How are we going to do it? So I just give you a quick one. So for example, right, alkaline. I use ammonia. Ammonia react with water. They will form ammonium ions. They will form ammonium ion, NH4 plus OH minus. Okay, this is alkaline. And you know, just now acid we have Ka, which is the ions over the acid molecule. For alkaline or for base, we have Kb. Kb, yeah. The A stands for acid, now the B stands for base. So for Kb, similar idea. It is the ions, the concentration of ions over the concentration of the alkaline or the base. We don't want water. Okay? So similar to acid just now, you see. Acid, we don't want the H2O. If you have H2O, it's Kc. So Kc is As syllabus. Now we seldom use Kc already. Okay, so we use Ka instead. No H2O concentration. So likewise, our Kb has no H2O concentration as well. Okay, so if you have Ka, right, then of course you will have something similar like just now we have pKa, right? Now we have pKb. So I just write down only. pKb is equal to negative log Kb. pKb, yeah. Okay, so that is one thing. And beside that, you see just now after Ka, right? After Ka, you can find pKa. Okay, of course you can also do it in the other way around. You can do Kb equal to 10 to the power of negative pKb. So this is similar to just now for acid. And then after that, right, you have pH scale for acid. Okay, pH scale for acid. So where you have to negative log the concentration of H plus to get pH. So now we have the similar versions. We have POH, where you have to negative log the OH minus. So again, just now I mentioned pKa, and as you can see here, pKa and pH, although they are formulas are found by similar concept, but they are not the same thing. They are different in value as in here. So likewise in base, pKb and pOH, the formula are more or less the same, but they are not same in value. Okay, so we have pOH for alkaline. So once you have pOH for alkaline, then we can use formula that we learned just now. 14 equal to pH plus pOH to find out the pH of alkaline. So I just write down also over here so that you have a set of formula for alkaline. Okay, so the formula is 14 equal to pH plus pOH. So because of that, the ionic product of water is important here because at the end it helps us to find out the pH of alkaline. Okay, so now let's see one example. I create similar example lah, similar to this one. Okay, similar to this one. Okay, example. Calculate the pH of 0.1 mole per dm cube of ammonia in aqueous solution, where they give you Kb of ammonia as 1.8 times 10 to the power of -5 mole per dm cube. Similar concept one. So it is not too hard to do it. As long as you follow back the same way like here, then you can get it. Okay, so we just do it straight away. First, we find pOH. We find pOH. You compare to just now. Just now we find pH. For acid, we find pH. Now for base, we find pOH. Okay, so let's say, okay, this is the question, and we find pOH. Negative log base 10 concentration of hydroxide, and we don't know concentration of hydroxide at this moment. Okay, so same like just now we don't know the concentration of H plus at the beginning, so we write down the equation and we work out the Kb, the Ka for this case. Now we work out the Kb. Okay, so let's say I just do it over here. Okay, I write down the equation. So the equation is ammonia dissociate. Okay, so I plan to write water on top but cannot. So I must write H2O here, so that it become NH4 plus and OH minus. So the Kb is NH4 plus OH minus NH3. So again, the problem here is we have to know that these two ions are in the ratio of 1:1. From the chemical equation here, we know this is 1:1. Okay, so that means the concentration of ammonium ions is the same with concentration of hydroxide ion. Okay, so I just put a mark here. Concentration of ammonium ions is equal to concentration of hydroxide ion. So because of that, I can replace it with hydroxide ions power 2. So imagine this thing you replace in front. We don't want the ammonium ion. The ammonium ion substitute by OH minus concentration. So hence it become power 2. And at the bottom, we keep the same thing. And now we substitute. Kb is 1.8 times 10 to the power of negative 5. The hydroxides, unknown. The concentrations of ammonia, 0.1. So we can get the concentration of hydroxide now. Which is 1.342 times 10 to the power of negative 3. Then we can find out the pOH by doing negative log of this value. Okay, so we negative log. So we get 2.872. So after you negative log, you get the pOH ready. But don't forget the formula just now, which is here. Once you get the pOH, then you can use 14 equal to pH plus pOH to find out the pH of the alkaline. So I write the formula first. 14 equal to pH plus pOH. So 14 equal to pH plus 2.872. Then the pH of ammonia is found. 14 minus answer, we get 11.1. Okay, let's say I keep it as 3 significant figure, 11.1. Okay, so that is how we do it for weak alkaline. And you will realize the working is more or less the same like the working for the weak acid just now, the ethanol acid. Okay, so we finish up this page already.